Good morning and welcome to our fifth lesson. This week we're going to have our third and final called line planes projections. First of all, let's talk about lines in space. To describe a line in three-dimensional space, we need two things. We need a point that the line passes through, and we need a vector which gives the direction of the line. Look at this picture. We have a point P0. The line passes through the point P0, and we have a vector V which tells us which direction the line goes past P0. Let P be any point on the line. The vector from 0 to P0 I want to call R0, and the vector from 0 P or from P I called R. The line, which I'm calling capital L, passing through the point P0 and parallel to the vector V, has the vector equation R is equal to R0 plus V. More useful to us are parameterized equation. X, Y, Z is a point on the line. Then X, Y, and Z must satisfy X is equal to X0 plus TV, Y is equal to Y0 plus TV2, Z is equal to Z0 plus TV3 for some number T. These equations are called the parametric equations for the line passing through the point P0 parallel to the vector V. Let's do an example. Let's slow down. You have a homework question similar to this example. Find parametric equations for the line passing through the point -2, 0, 4, parallel to the vector 2 plus 4, 2i plus 4j minus 2k. We need three equations. X is equal to, Y is equal to, and Z is equal to. First, we look at the point that the line moves. The line passes through the point -2, 0, 4. We put these numbers first in each equation. X must be -2 plus something, Y must be 0 plus something, and Z must be 4 plus something. Then we look at the vector, 2i plus 4j minus 2k. So let's look at the first number, the 2. That tells us in the equation for x, we must have plus 2t. The vector has plus 4j. So in the equation for y, we must have plus 4t. And finally, the vector v also has minus 2k. So the z equation must include minus 2t. Put this all together. X must be -2 plus 2t, y must be 4t, and z must be 4 minus 2t. Here is a picture of this line. When t is equal to 0, take the equations, replace t by 0, we get x is -2, y is equal to 0, and z is equal to 4, which is the point we're supposed to be passing through. And then for each value of t in the real numbers, we have a point on the line. For example, if t is equal to half, we're at this point on the line. T is equal to 1, we're at this point. T is equal to 3 over 2, we're at this point, etc. We can go the other way. T is equal to minus 1, then we're going to be at this point on the line. In this picture, I've also drawn the vector v. You can see that the line is parallel to the vector v. Another question. Find parametric equations for the line passing through the point minus 3, 2, minus 3, and the point 1, minus 1, 4. We need a point on the line, and we need a vector which is parallel to the line. For a point on the line, we have two choices. We could either choose P or we could choose Q. Both would give a correct answer. For this example, I'm choosing to take point P. We also need a vector which is parallel to the line. We have this line that passes through the point P, passes through the point Q. We need a vector which is parallel to the line, and we might as well take the vector from P to Q, which we can calculate is 4i minus 3j plus 7k. After we have our numbers, we can write down the equations. Our point is minus 3, 2, minus 3. Put these numbers first. X is minus 3 plus something, y is 2 plus something, z is minus 3 plus something. And then look at our vector, 4i minus 3j plus 7k. X must have plus 4t, y must have minus 3t, and z must have plus 7t. Previously, we had an equation for a line in which t could be any real number. Let's suppose instead of saying t can be any real number, we restrict t to be between a and b. Then instead of a line which goes all of the way to infinity in each direction, we have a line segment. We have a line which has two ends. At one end we will have t is equal to a, and at the other end we will have t equal to b. Parameterize, that's another way to say find the parametric equations. A line segment joining P and Q. This is the same points P and Q as previously. So we already know x is minus 3 plus 40, y is 2 minus 3t, and z is minus 3 plus 7t. We can say that when t is equal to 0, we get minus 3 to minus 3, or in other words, we get p. And when t is equal to 1, we get minus 3 plus 4, or 1, 2 minus 3, or minus 1, minus 3 plus 7, which is 4. In other words, when t is equal to 1, we get 1 minus 1. 4. Therefore, the answer to this problem, the line segment is x is minus 3 plus 40, y is 2 minus 3t, z is minus 3 plus 7t, where t is between 0 and 1. Here's a picture of this line segment. It's the line joining the point P and the point Q. We can calculate the distance from a point to a line. Let's suppose we have some point S and we have a line L, which passes through the point P and which is parallel to the vector P. I want to calculate the shortest distance from the point S to the line L. For the shortest distance, we would be measuring this dotted line where this angle which I'm pointing to must be 90 degrees. So the question is, in this picture, how do we calculate the distance D? Let me go back. Now we have an angle. We have the angle theta. We know that the length of this vector is the norm of PS. Therefore, in this picture, D must be norm of PS multiplied by sine of the angle. Just high school trigonometry. D must be the norm of PS multiplied by sine theta. But let me remind you, we have cross product formula. PS cross V is the norm of PS, norm of V sine theta n, where n is a unit vector. In other words, the norm of the vector n is equal to 1. So if we take the norm of both sides of this equation, the norm of PS cross V, norm of PS is already a positive number, we can leave that. Norm of V is going to be a positive number. Sine theta must be a positive number. And the norm of n is equal to 1. So we get the norm of PS cross V is the norm of PS, norm of V sine theta. Therefore, the distance D must be the norm of PS cross V divided by the norm. And this is the equation which we need to remember. If you're asked to find the distance from a point to a line, you will be using this formula in the box. So, find the distance from the point 115 to the line x is equal to 1 plus t, y is equal to 3 minus t, z is equal to 2t. We go back one slide. We want to use this formula. We need a point P on the line and the vector v which is parallel to the line, and then we will put them into this formula to calculate the distance. For the point on the line, we look at the first numbers, 1, 3, and here 0. The line must pass through the point 1, 3, 0. To say this another way, replace t by 0 to find the point 1, 3, 0. We also need a vector. For the vector, we look at the numbers in front of the t. The numbers are 1, minus 1, and 2. So our vector must be 1i minus 1j plus 2k. We calculate the vector from P to S by calculating S minus P, and we find this is minus 2j plus 5k. And then we calculate the cross product of PS with V. Using the formula from last week, you should check this, practice with your cross product. We find that PS cross V is I plus 5j 2k. Therefore, we can put this into our formula. The norm of PS cross V we can calculate as the square root of 30. The norm of V we calculate as the square root of 6. Square root of 30 divided by square root of 6 is equal to the square root of 5. The distance from this point to this line is the square root of 5. Sometimes you might have two lines which intersect at point P. Precisely, two lines intersect at a point P if and only a point P lies on both lines. For example, following two lines intersect, if yes, where? X is 7 minus t, y is 3 plus 3t, and z is equal to 2t. Line 2, x is equal to minus 1 plus 2s, y is equal to 3s, and z is equal to 1 plus s. Two different lines, so I'm going to use two different letters for the variable in the line. I'm using t for the first line. That means I can't use t on the second line. I need a different letter. I'm choosing to use s for the second line. The two lines intersect if and only if we can find numbers s and t such that these three equations are all true. X must be 7 minus t and x must be minus 1 plus 2s. In other words, 7 minus t must be the same as minus 1 plus s. 3 plus 3t must be y and also equal to 3s. 2t must be z and also equal to 1 plus s. From the first equation, we can rearrange this and see that we must have that t is equal to 8 minus 2s. And then we put this into the second equation. So from the second equation, we can rearrange this, and we can find that s must be t plus 1. If we put the first equation into the second equation, we have 8 minus 2s, s is t plus 1, so we have 8 minus 2s plus 1, or 9 minus 2s. Take the minus 2s to the left, we get 3s is equal to 9, which means that we must have the s is equal to 3, and then we must have t equal to 2. If s is 3 and t is equal to 2, then the first two equations are true. We're asking, do the following two lines intersect? Now we must look at the third equation. If the third equation is also satisfied, then the two lines intersect. If the third line is not true, then the two lines do not intersect. So we look at the third equation. 2t is equal to 4 and 1 plus s is equal to 4. This is also satisfied. Because all three equations are all true for this value of s and this value of t, the lines must intersect at this value of s and this value of t. Putting these s and t into the equations, we find the point where they intersect. Another example. Do these two lines intersect? And if the answer is yes, where? We start with three equations. X must be 1 plus t and x must be minus 1, 2s. Y must be 3t and 3s. If 3t is equal to 3s, then s equals to t. And the third equation, 3 plus 3t must be the same as 1 plus s. Is it possible to find s and t such that all three equations are true? The second equation tells us that s must be equal to t. If we then look at the first equation, we find that t is equal to, but if we look at the third equation, we find that t must be minus t. And we can't have this. We can't have t is 2 and t is minus 2. That means it's not possible to find s and the t such that all three equations are true at the same time. Hence, these two lines do not intersect. We might be interested in measuring the distance between two lines. There's three cases to consider. Maybe the two lines intersect. Here's a picture. Two lines intersect, then this is answer. This is easy. The distance between the two lines is 0 because they're intersecting. Maybe the two lines do not intersect and they're parallel. The lines are parallel if the vector from line 1 is equal to some number multiply the vector for line 2. Or maybe the lines do not intersect and they are skewed. I'm drawing like this. So imagine that line 1 is somehow above line 2. I've tried to show this by hiding part of line 2. Intersecting lines, this is the easy one. If our two lines intersect, then clearly the distance between them is 0 because they're touching. Next, parallel lines. We can imagine that we have a picture something like this. Line L1 passes through the point P1, parallel to V1. Line L2 passes through the P2, parallel to the vector V2. The distance between two lines is the same as the distance from the point P2 to the line L1. We already have a formula for the distance from a point to a line. We use the same formula again. Distance between these two lines is P1, P2 cross V1 divided by the norm of V1. Skew lines. Imagine we have a picture something like this. Again, the line L1 passes through P1 parallel to V1, and the line L2 passes through the point P2 parallel to Q2. We're trying to find the smallest distance between these two lines. So let's imagine there's some unknown point Q1 on line 1, which is closest to line 2, and there's some unknown Q2 on line L2, which is closest to L1. And the distance D that we want will be distance between Q1 and Q2. It's maybe difficult to see in this picture, so let me draw on the left. If this is the line L2, then the dotted line at Q2 must be at 90 degrees to L2. Likewise, the dotted line must be at 90 degrees to the line L1. We need to find a vector which is both orthogonal to line 1 and orthogonal to line 2. So what we do is we take V1 cross V2. Remember from last week, V1 cross V2 is always orthogonal to V1 and it's orthogonal to V2. So this vector is orthogonal to both the lines. In other words, this vector must be parallel to the line from Q1 to Q2. Now we can calculate the distance. That's the norm of the vector from Q2. This is the same as the projection of the vector P1 on N. Part of the vector P1 from P1 to P2 points in the same direction N. We have a formula for the projection of a vector onto a vector. Take the norm of this formula, we get the absolute value of P1, P2 dot N divided by the norm of N. That's why this formula is the formula that we need, the formula that you will need in the exam if I ask you a question like this is the distance between skew lines is the absolute value of P1, P2 dot V1 cross V2 divided by the norm of V1 cross V2. So let's recap. Here's an interesting slide which you might want to have to your hand during the exam. The distance between intersecting lines must be 0. The distance between parallel lines is given with this formula, and the distance between skew lines is given with this formula. Parallel lines is when one vector is equal to a multiple of the other vector. That's the same as saying that their cross product is the 0 vector. If the cross product of the two vectors is not the 0 vector, then we know that we must have skew lines. For example, find the distance between the following two lines. Line 1, x is 0, y is minus t, z is equal to t. Line 2, x is equal to 1 plus 2s, y is equal to s, and z is equal to minus 3s. First, we need a point on each line. We can do these from the equations. And we need a vector which is parallel to each line. Again, we can read these straight from equations. Then we calculate V1 cross 2. And we get 2r, 2j plus, which is the 0. If this was equal to 0, parallel vector, but this is not 0, which means that these two lines are skew. Moreover, we can find the vector from P1 to P2 from 0, 0, 0 to 1, 0, 0 is equal to I. And then we're ready to use the formula. The formula from the previous page, the formula which you will remember for the exam, or you will make sure you write down and have next year for the exam. Absolute value of P1, P2 dot V1 cross V2 divided by the norm of V1 cross V2. Put in everything that we have. We have I dot 2I plus 2J plus 2K divided by the norm of 2I plus 2J plus 2K. I dot this vector, that's 1 multiplied by 2, plus 0 multiplied by 2, plus 0 multiplied by 2. This gives us the absolute value of 2. On the bottom, the norm of this vector is the square root of 2 squared plus 2 squared plus 2 squared, or square root of 12. 2 divided by the square root of 12 is the same as 1 divided by the square root of 3. The answer to this question is the distance between these two lines is 1 divided by the square root of 3. Next, planes. To describe a plane, we need a point P0, which the plane passes through, and we need a vector n, which is perpendicular to the plane. Here is our picture. We have some point P0 on the plane. I've only drawn a small part of this plane. Of course, this plane goes to infinity in each direction, goes all of the way off this in each direction. I've only drawn a small part of this plane. The vector n, which is a vector which is orthogonal or perpendicular to the plane, a vector where all of these angles around the vector is 90 degrees, is called a normal vector. And let's suppose the point x, y, z is just any point on the plane. Then the vector from P0 to P must be orthogonal to the vector n. In other words, n dot P0P must be equal to 0. If we use coordinates, that's the same as a x minus x0 plus b y minus y0 plus c z minus z0 is equal to 0. Or if we rearrange this, we get the formula in the box, the standard equation for a plane. Ax plus by plus cz is equal to d, where a, b, and c come from the normal vector n. For example, find an equation for the plane passing through the point -3, 7, 0, 7, normal to the vector 5i plus 2j plus k. We start with our standard equation for a plane. A x minus x0 plus by minus y0 plus c minus z0 is equal to 0. And we put the numbers in. Our point is -3, 0, 7. We put these in place of x0, y0, and z0. So we have -3 here, 0 here, and -7 just here. From the normal vector n, our numbers are 5, 2, and -1. Put these in the place of capital A, capital B, capital C. We get 5, 2, and a -1. Rearrange this equation and simplify, and we get our answer. 5x plus 2y minus z is equal to -22. Of course, it's 5, 2, minus 1 because the normal vector had 5, 2, minus 1. This calculation is just to find the number minus 22 because the numbers on the left we always know are going to be the same as the numbers in the normal vector. Let me repeat that. The vector a plus pj plus a is normal to the plane ax plus by plus cz is d. So, for example, if I asked you, find a vector normal to the plane x plus 2y plus 3z is equal 4. We don't need the number 4, that doesn't matter. We're looking at the numbers on the left. The number 1, the number 2, and the number 3. And then straight away we can write down the answer. The normal vector is I plus 2j plus 3k. Find an equation for the plane containing the points E, F, and G. To find the equation for a plane, we need a point on the plane. We could choose any of these. I'm going to choose E. And we need a vector which is normal to the plane. We can take EF cross EG because this vector is perpendicular to EF. This is EF. This will be N. This was 90 degrees. And N is also perpendicular to EG. So we calculate that N is EF cross EG. When you have time to read the lecture notes or rewatch these videos, you can check this calculation and check that N is 3i plus 2j plus 6k. So then straight away, we know that the final answer will be 3x plus 2y plus 6z is equal to something. To find the something, we use a point on the plane. I'm going to use the point 0, 0, 1. Put this into the equation, 0, 0, and 1. And we find that the something is going to be equal to 6. Suppose we have two planes, two possibilities. Either the two planes are parallel. We know two planes are parallel if n1 is equal to some constant multiplied by n2. That's the same as saying that n1 cross n2 is equal to the 0 vector. Or two planes intersect in a line if and only if n1 is not a multiple of n2, or that's the same as saying that n1 cross n2 is not the 0 vector. Let's suppose we have two planes and we're trying to find the line where they intersect. For a line, we need a point on the line, and we need a vector which is parallel to the line. The vector which is parallel to the line must be orthogonal to n1, and it must be orthogonal to n2. If we're trying to find a vector which is orthogonal to both n and n2, we can take n1 cross n2. Because n1 cross n2 is always orthogonal to n1 and orthogonal to n2. There we go. Find a vector parallel to the line of intersection of the plane. 3x minus 6y minus 2z is equal to 15, and 2x plus y minus 2z is equal to 5. On the first plane, the numbers are 3, minus 6, and minus 2. So the normal vector is 3i minus 6j minus 6k. On the second plane, our numbers are 2, 1, minus 2. So our second normal vector is 2i plus j minus 2k. The answer to this question, a vector which is parallel to the line of intersection, we're going to take n1 cross n2. And I'm going to leave it for you to check that when we cross these two vectors, we get 14i plus 2j plus 15k. Here's another idea. Let's suppose we have a plane and a line. And let's suppose the line is intersecting the plane at some point, which I'm going to call P. I want to find this point P. Find the point where the line 8 over 3 plus 2t, y is equal to minus 2t, z is 1 plus t, intersects the plane 3x plus 2y plus 6z is equal to 6. What we do is we start with the equation of the plane, 3x plus 2y plus 6z is equal to 6. But we know a formula for x. We know that x is 8 over 3 plus 2t. So instead of writing x, we write 8 over 3 plus 2t. We know that y is minus 2t. So instead of y, we write minus 2t. And we know that z is equal to 1 plus t. So instead of z, we write 1 plus t. After we rearrange this equation and simplify it, we find that t must be minus 1. The line intersects the plane and t is equal to minus 1. In other words, we're looking for the point x, y, z when t is equal to minus 1. We're looking for 8 over 3 plus 2t, minus 2t, 1 plus t, when t is equal to minus 1. Put t equal to minus 1 into here. We have the point 2 over 3, 2, 0. We might calculate the distance from a point to a plane. Look at these pictures. I have a three-dimensional picture, two-dimensional picture. I'm trying to calculate this distance d, which is the smallest distance from the point S plane. And from this picture, we can see that this distance is the same as the length or norm of this vector, the projection of PS onto N. So this gives us our formula. The distance from the point S to the plane containing the point P with normal vector N is absolute value of PS dot N divided by norm of N. Remember, PS dot N is a number. For number, we use these single vertical lines. N is a vector, so we use double vertical lines around N. For example, find the distance from the point 1, 2, 3 point, so to the plane x plus 2y plus 3z is equal to 4. First, we need to find a point in this plane. We need some numbers x, y, z which satisfy the equation for a plane. And of course, there's infinitely many points that we can choose. But an easy way to do this is to say, let's have y equal to 0 and z equal to 0, and then let's calculate x must be 4. If y is 0 and z is 0, then x must be 4. 0.400 satisfies the equation for a plane. This is a point in the plane. Finding the normal vector is easy. N is I plus 2j plus 3k. And then we use the formula, and I'll leave it for you to check that this distance is 10 divided by the square root of 14. We might be interested in the angle between two planes. And straight away from this picture, you can see there's two different angles between the plane. We might have this angle theta, or we might have this angle 180 degrees minus theta. We want to take the smaller number. Whichever of these two angles is smaller, we're going to call the angle between two planes. You will also note that this angle theta is the same as the angle between N1 and N2. We know how to find the angle between two. The angle between two planes is equal to whichever one of the following numbers is smaller. The angle between N1 and N2, or 180 degrees minus this angle. That means that the angle between two planes will always be between 0 and 90 degrees. For example, find the angle between these two planes. First, we write down the two normal vectors. We know how to do this. And we calculate the angle between these two vectors using the formula from last week. And we find that the angle is approximately 101 degrees. We want to find an angle which is between 0 and 90 degrees. So this is not the angle that we want. We want the angle 180 minus 101 degrees. The answer is 79 degrees. Our final section for today is a long section. I'm going to be another 20 or 30 minutes talking about this. Would you like a 10-minute break before I continue? Okay, lots of people would like a 10-minute break, so I'm going to take a break and I will see you at 10:05. Okay, let's continue. Our final chapter for today is projections. Last week we talked about projecting a vector onto a vector. Now we're going to be talking about projecting things onto lines and onto planes. Last week we defined projection of a vector u onto a vector v using this formula. We're going to be using this formula quite a lot in this chapter. If we have a line L and a vector, let's say PS in the picture, we can project the vector onto the line. You can think about this in two different ways. You can imagine that we have the sun up here, perpendicular to the line, and we can look to see what is the shadow of our vector PS. The shadow of the red vector in this picture is green. Or there's another way to think about this. We might imagine that we have this picture and we have some very heavy weight which we put on top, and it squashes everything downwards. How does it squash the red vector down onto the line? It squashes the red vector down to the green line. The red vector squashed down onto the green vector. And of course we can say the projection of a vector u onto the line L is the same as the projection of u onto a vector v which is parallel to a line. We already have a formula for the projection of a vector onto a vector. We use the same formula for the projection of a vector onto a line. For example, find the projection of the vector u onto this line. The projection of u onto the line is the same as the projection of u onto a vector v, which is parallel to the line. Using the formula, I want to be quick here. I leave this for you to check. We get minus 2 over 3i plus 1 over 3j plus 4 over 3. Please take your time when you read the lecture notes to read through this and check that this is correct. Or we might project a vector onto a plane. Again, let's imagine that we have the sun up here and we're looking for the shadow of the vector u. Or let's imagine that we have something heavy on top which is pushing down and squashing the red vector u onto the plane. We're trying to find this green vector, the projection of u onto the plane. And we can see from this picture, the green vector, perhaps I can use some colors. Yes. This green vector is equal to the red vector u minus the orange vector. Or to say this another way, green vector plus orange vector is equal to red vector. The projection of u onto the normal vector n, projection of a vector onto a vector we know. We have u minus this vector, or u minus u dot n over the norm of n squared multiplied by n. This is the formula. Make sure you make a note of this before the exam. Let's do an example. Find the projection of the vector u onto the plane. The formula is that the projection of u onto the plane is u minus the projection of u onto n. So first we calculate the projection of u onto n. Projection of a vector onto a vector, we know how to do this. The answer is 3 over 2i minus 1 over 2j plus k. Therefore, the answer must be minus a half I plus 5 over 2j plus 2k. Again, I'm being deliberately quick here. You can check this later. Projection of a point on plane. Suppose we have a point P, we have the sun up here, and we're asking where is the shadow of the point P? Here it is. Here is the shadow of the point P on the plane. Projection of point P onto plane. And you can see from this picture that if we know the projection PQ onto N, we can just do P plus this vector to get the answer. Start at P, do the orange vector, and we end up at the answer. The projection of a P onto this plane is P plus the projection of PQ onto N, where Q is some point in the plane. For example, find the projection of the point 1, 2, minus 4 onto the plane. 2x plus y plus 4z is equal to 2. We need a vector which is normal to the plane. Straight away, we write that down. Numbers in the plane, equation of 2, 1, 4. So we must have the normal vector 2i plus j plus 4k. We also need a point on the plane. You can use the trick that I showed you before. Let's suppose that y is 0 and z is 0. And then we're left with 2x is equal to 2 or x is equal to 1. We can take the point 1, 0, 0 in the plane. You can take any point in the plane that you want. If you want to, you can say, let's say x is 0 and z is 0, and then we'll choose y equal to 2. And then you would get the point 0, 2, 0. That's also a point on the plane, and that would also give the correct answer. The vector from P to Q we can calculate is minus 2j plus 4k. Projection of PQ onto N is the formula for projection of a vector onto a vector again. When we use this formula, when we put the numbers in and calculate this, we get 4 over 3i plus 2 over 3j plus 8 over k. And then we're almost finished. We want to do P plus the projection of PQ onto N. Point P is 1, 2, minus 4. We've just calculated this vector is 4 over 3i plus 2 over 3j plus 8 over 3k. Or the point 4 over 3, comma 2 over 3, comma 8 over 3. Add these together and we get our answer. 7 over 3, 8 over 3, minus 5 over 3. Now, if we haven't made any mistakes in our calculation, this is the correct answer. But it's always worth doing a quick check if you have a spare minute. If you finish a few minutes before the end of the exam and you want to double check that your answer is correct, always worth doing a quick check whenever you can. For this type of problem, we should do a quick check that our answer really is in play. And this will give us an idea as to whether or not our answer is correct or not, if we've made any mistakes or not. So to do this quick check, we start with 2x plus y plus 4z, and we're going to put the numbers 7 over 3, 8 over 3, minus 5 over 3 into this, and we calculate this is equal to 2, which is what we should have for this plane. So it looks like there's no mistakes in this calculation. It looks like the answer is correct. If you have a free minute or two, it's worth doing a quick check like this so that you know that your answer is probably correct. We can also project a line onto a plane. And there's going to be 3 cases we need to talk about. Case 1, the line is orthogonal to the plane. This is the case we will have when the vector v is parallel to n, or v cross n is equal to the 0 vector. Case 2, we need to talk about what happens if the line is parallel to the plane. We know that a line is parallel to the plane if v dot n is equal to 0. In other words, if the vector v is orthogonal to n. Let me just say this again. The dot product of 2 vectors is equal to 0. Then these 2 vectors must be orthogonal. The cross product of 2 vectors is equal to 0. Then these 2 vectors must be parallel. Or case 3, the line is not parallel. The line is not orthogonal to it. V dot n is not the number 0. V cross n is not the 0 vector. First, let's suppose that the line is orthogonal to the plane. We have a picture like this, and this angle where the line crosses the plane, it must be 90 degrees, however we measure this. This is the easiest case. The projection of the line, and you can think about this by imagining that there is a sun at the top. Where is the shadow of the line on the plane? The answer is it's only this point here. Projection of the line onto the plane, the shadow of the line onto the plane, is just the point where they intersect. So the projection of the line L onto the plane would be the same as the projection of the point P onto the plane. Case 2. Let's suppose we have a line which is parallel to a plane. Again, let's imagine we have the sun at the top, and we're looking for the shadow of the red line on the plane. The shadow of the red line on the plane is this black line. The black line is passing through this point, the projection of P onto the plane, and the line is parallel to L. You have the same vector v here. Vector v and the vector v. Same vector because these 2 lines are parallel. So we can say that the projection of the line L onto the plane is the line passing through this point in the direction of v. So really we're calculating the projection of P onto the plane, and then we're writing down the line equations using the same vector V. And finally, what is the projection of the red line onto the plane, or the shadow of the red line onto the plane? This line must intersect the plane at some point. Let's call this the B. Point B is on both the red line and its projection on its shadow. And we can calculate another point on the black line. This is the point projection of P on the plane. We know 2 points on the black line. The black line must be the line passing through these 2 points. In this case, the projection of the red line onto the plane is the line which passes through the point B, and the projection of P onto the plane. I have 3 examples. Find the projection of this line onto this plane. And I'm going to go through step by step. The first thing to do is to write down a vector v which is parallel to the line, and a vector n which is normal to the plane. We know how to do this. Step 2. Does the line intersect the plane? Well, think about the pictures. We might have orthogonal, we might have parallel, or we might have case 3 where the line looks like this. If the line is parallel to the plane, then it does not intersect the plane. If it's not parallel to the plane, then it must intersect the plane somewhere. So really we're asking, is the line parallel to the plane? To decide if it's parallel, we calculate v dot n, and in this case we find that v dot n is not 0. So the line is not parallel to the plane. The line does intersect the plane somewhere. Step 3, find the point of intersection. I've shown you how to do this in an earlier example. We start with the equation for a plane, and we substitute in the line equations for x, y, and z. Rearrange this to find t, and then put t into the line equations to find the point B, 9.4, 3, 5.2. So, what do we know so far? We know that the line intersects the plane, might be orthogonal, or it might not be orthogonal. And we know this point where it intersects is the point 9.4, 3, 5.2. Next we ask, is the line orthogonal to the plane? Decide if a line is orthogonal to a plane, we calculate v cross n. And I will leave for you to check that v cross n is the 0 vector. Because this is 0, the answer is yes. The line is orthogonal to the plane. So now we know that the picture looks like this. The line is orthogonal to the plane, and we know this point B where the line intersects the plane. And that's all we need to do. The line is orthogonal to the plane. The projection of the line onto the plane is just the point where the line intersects the plane. Another example. Find the projection of this line onto this plane. Start as before, write down V and N, and then answer the question, does the line intersect the plane? In other words, is the line parallel or not parallel to the line? To answer this, we calculate V dot N, and in this case, we get 0. Therefore, the line does not intersect the plane, the line is parallel to the plane. So now we know our picture looks like this. We're going to project a parallel line down onto a plane, and we're going to find this point. We know that the vector which is parallel to the line we start with will also be parallel to its projection. All we need to do is to find some point on the projection. So find a point on the projection of the line onto the plane. The point 1, 2, 3 lines on the original line, on line L. The point 900 lies on the plane. So PQ is ATi minus 2j minus 3k. And the projection of PQ onto N is a half N. I'm being quick here, you can check this later. Therefore, the projection of the point P on the plane is going to be P plus the projection of the vector PQ onto N, and we can calculate this is 5 over 2, 4 minus a half. Before we go on, let's do a quick double check. Is this point really on the plane, or have we made a mistake? 3x plus 4y minus 7z. Put these numbers in and we get 20. The answer is yes, this point really is on the plane, so probably we have not made a mistake. And then finally, find the projection of L onto the plane. We are looking for the line which passes through 5 over 2, 4 minus a half in the direction 4i plus 4j plus 4k. As soon as we know that, we can write down the parametric equations for the line. Find the projection of the line 15, x is 15 plus 15t, y is minus 12 minus 15t, z is 17 plus 11t, onto the plane 13x minus 9y plus 16z is equal to 69. We start in the same way. Find v and n, you know how to do this, and then answer the question, does the line intersect the plane? We calculate v dot n, and we find that this is not 0. The line is not parallel to the plane, it must intersect the plane somewhere. So either the line is orthogonal to the plane, or we have a picture like this. Find the point of intersection. I've showed you how to do this. Please spend the time to double check this type of calculation until you're happy with it. I find the point 0, 3, 6. Is the line orthogonal to the plane? To answer this, we calculate the cross product of V and N, and you can check that we get minus 141i minus 97j plus 6k, which is not a zero vector. So the line is not orthogonal to the plane. Now we know that the picture looks like this. And we know this point B where the line intersects the plane. Step 5, we need to find another point on the projection of the line onto the plane. Draw the picture again. We have something like this. We have a point P on the original line. We want to project down and find the projection of P onto the plane. I've showed you how to project a point onto a plane. You can go through this calculation and you can check that the projection of the point P onto the plane is 2 minus 3, 1. And then we have everything that we need. We know this blue point on the black line. We also know the black point. We need to find the line which passes through the blue point and the black point. In the first chapter today, we saw, I think in the second example, how do we find the line passing through 2 points. You can check that the answer to the question is x is equal to 2t, y is equal to 3 minus 6t, z is equal to 6 minus 5t. In this chapter, I've tried to be very quick and just point out the important parts in each example, but I'm leaving the details for you to check at a later date. If anything is unclear, if you want extra help on any of these examples, please ask me in the discussion forum after you've read through the lecture notes. That is the end of our topics of geometry. Next week, we're going to be talking about combinatorics, which means counting, and then we're going to start talking about probability. Can I upload the vector slides? Yes, I will do that later today. The slides are basically the same as the lecture notes, but the lecture notes are good for printing out. Slides are good for reading on a screen. Are all the topics coming in the midterm? Yes. The midterm will cover every topic that we talk about before the midterm exam. So that will be everything that we cover between weeks 1 and week 8. So it's going to be all of geometry, all of combinatorics, and all of probability. This is the end of the lesson. I'm ready to answer your questions. You're welcome to leave whenever you wish if you don't have questions. Second week slides are the graph. Weeks 1 and week 2 were really an introduction, or I want to revise high school math, things that we will need for later. When we do calculus later in the semester, we're going to be doing functions. So when we do calculus, this idea of these graphs can be important. For geometry and probability, graphs of functions are not well. So there will be a question about them in this midterm. No, the midterm exam questions will all be about geometry and combinatorics and probability. Of course, you should study part 1 of this course because we rely on the notation things in part 1, but I'm not explicitly going to ask questions about the first section. Will we get a formula sheet? No, but you can make your own. If you really want a formula sheet, I can prepare one for you. I wasn't planning to. If I have a formula sheet prepared, if you tell me if you want one, and I will make it available to you before the exam. Okay, well then I will upload my formula sheet that I have from last year, and you can print it out if you want. And if you think there's anything missing from the formula sheet, you can write it on yourself. Okay, if you check the course material section, you should find last year's formula sheet. There's some rules on the top of the sheet which were relevant last year. They're not relevant for you because your exam is online, so you can ignore that. It's possible that you might find a formula in the lecture notes which you think you will need, which is not on the formula sheet, in which case you can write it on yourself. Are there any more questions? Okay, if there are no more questions, then let's finish the lesson here. You can ask me questions on the discussion board later if you think of any.